the time maybe 1000 Kelvin and below. So in this case, the next major difference between a solar cell and a TPV cell is that a TPV cell is very near to the heat source. It can be from nanometers to centimeters or even meters. But if you look at a sun, which is a solar spectrum, it needs to travel all the way more than millions of kilometers to reach the Earth, and then solar cell will convert that. So in terms of control of the radiation photons, certainly TPV cell is much easier because you are much nearer to the source. But in terms of the abundance and also in terms of the the total radiation power, certainly sun is still giving a much higher power. It's just that it is covering a very large area. So how does it look like in terms of spectrum? So we have a spectrum here of a sun radiating at 6000 Kelvin. The sun is concentrating more in the spectrum of below 1000 nanometers. So we can see here, you have a little bit in the 1000 nanometers and above, but not that much. So mainly in the visible region before 1000 nanometers. Compared to that, TPV radiation spectrum is looking at anything, much above 1000 Kelvin. So you can see that depending on the temperature, it will shift towards the right. The lower the temperature, the longer the peak wavelength. So in terms of that, you are looking at material that needs to be able to absorb photons in wavelength more than 1000 nanometers. So I wouldn't go into details regarding wavelength. I suppose most of us are very familiar with wavelength. So the next thing here, we talk about the band gap, because you need to have band gap that can absorb, semiconductor material with the correct band gap that can absorb photons more than 1000 nanometers. And most of the time, we are looking at more than 1500 or more than 2000 nanometers for us to efficiently harvest all these radiated photons. Right. I think in terms of radiation source temperature is quite straightforward. In terms of gap distance, it is also straightforward. But I would like to elaborate a little bit more in terms of semiconductor material, where we say, when you have a silicon, you can actually harvest. You have a band gap of about 1 eV, 1.1 eV. You can harvest photons up to about 1000, 1100 nanometers. But when you are looking at TPV spectrum, we need to go, in a lower or narrower band gap material. And this is the region that we are looking at. That's why in our research later on, you will see that we are focusing more in terms of gallium antimonide. We are looking at indium gallium arsenide, which have a band gap of about 0.74 eV. And we also look at, other types of indium gallium arsenide and indium gallium arsenide antimonide to push the band gap of the semiconductor into even narrower region, so that we can harvest photons up to all the way to about 3000 nanometers. And that is the difficulty that I mentioned earlier in the first introductory slides, to say that, when semiconductor just started, people are focusing more in the shorter cutoff wavelength, easier to grow because of the band gap is much larger. So we believe that 30 years of gap is due to technology and constraint and limitation. Certainly by 1990s, it starts to improve and things become much better. And that's why starting from 1990 or late 80s, we start to see that TPV again gain the attention of the researcher from the world. So this is where we say that we used to concentrate this. This is for solar spectrum. And now we are looking at this part, the blue circle, where it is more for the TPV spectrum. So that is a little bit on the science, but generally, we have explored several applications, and one of the very well established paper and also report on the application has been in the steel mill. I think everyone knows that in the steel mill or plants, you have a lot of waste heat. They need to heat up the steel up to almost 1100 to 1200 degrees Celsius. And JX Crystal, a company in the UK, has taken the initiative to do a gallium antimonide TV cell. They produce more than 1 watt per centimeter square, meaning a centimeter square of steel, heated steel. The heat radiated, you can use a TPV cell to harvest 1 watt or slightly more than 1 watt at one time. Now, the beauty of TPV cell is that as long as the heat source is there, you always harvest it 24 hours. Unlike the solar spectrum, right? You have limitation in terms of hours, probably 4 to 5 hours is realistic. But TPV, as long as the process is going, the steel mill is operating, the heat radiation is always there. So with that kind of estimation for 1 watt per centimeter square, they are looking at the world steel production of 1,500 million metric tons. And from there, the calculation comes to almost more than 3 gigawatt at one time. So in terms of hours, times 24, and if you have 365 days, you get the numbers of energy produced. Obviously, then the number sounds interesting, but the implementation may be difficult in terms of cooling the module, in terms of making sure the reliability. However, all these are accompanying problems for TPV, where you just want to establish that particular power output first before you invest on all the other parts of it. So in our research work, we are going to show also how we can do all these things. But we were exploring mainly into thermal power plant, and we have done some study by visiting and also by exploring different system in a thermal power plant. And we realize there are plenty of areas for us to do uh, waste heat harvesting. Yeah, in just a small power plant, you have temperature up to about 700, 800 Kelvin. This is quite a normal area where people don't really worry too much about their insulation and things. That's why you have so much of waste there. So this is just a picture where we have taken from a thermal power plant. We see that easily you can get temperature of 500 Kelvin to about 7 to 800 Kelvin. We have also done a study or investigation from a fertilizer plant where they have a small generation of power also. Again, from there, you are looking at about 800 to 900 Kelvin of waste heat temperature. So these are area again. These are area that people don't care about them. These are waste heat that you don't want to release. They release it into the environment, but we don't want them to release into the environment. At least at the same time, if we can implement TPV cell, we can convert if even 1% to 2% of the whole wasted heat energy, you can get a lot of energy from there. So this is another application. But if you look at a wider scope from the literature, the previous 2-3 slides was from our investigation at the real sites. But from the literature, you also look at a lot of other possible application, such as in EV, in vehicle. You have a lot of waste heat actually at the exhaust area. Some of the work also looking at how we can concentrate the solar from the sun spectrum using a concentrated dish, and then after that we can again use a TPV cell. I won't go into detail why not we just harvest it using a solar cell. There are a lot of advantages and disadvantages that we can discuss, but these are the potential. And probably if you are interested later on, we can go into detail of each one of them, either one of them that interest you. So generally, applications are there. We need to make it possible by showing people the potential, and from there, further investment needs to be done to make the module feasible for their reliability, especially in terms of the heat management. Now, let me just go directly into our work. So far, we have looked at a TPV. We say that it can do this and that, especially in terms of energy to electricity conversion. But in our work, we are mainly focusing at the cell. Even though in a full TPV system, it should consist of, from the source to the emitter, and then from the emitter to some filters. But in our work, we are looking at the cell. Reason is because if you can increase the cell efficiency, you know how to design them to efficiently capture all the radiation photons, then the others can come in later. So our focus is on the cell. And in this case, we are looking at the spectrum where we are looking at spectrum of more than 2000 Kelvin. Therefore, as we said, you cannot just use a silicon or a gallium arsenide, but a silicon will only harvest, very small portion of our radiation photons. So this cell, we are looking at indium gallium arsenide cell. We are looking at gallium antimonide cell. Recently, there is a lot of interest in terms of germanium because it's much cheaper and easier to grow. So there are also some other groups looking at germanium. But we want to also push the limit to longer wavelength. So later on, we will look at what are the other materials that we are looking at. So a little bit on the experimental setup, right? We have a very small setup in University Tenaga Nasional, sponsored by TMB, for us to work on this TPV cell. So basically, these are very normal, and I suppose everyone quite used to characterizing different material, lasers, and things like that. So these are just some of the equipment that we have, probe station, and also some of the optical measurement units that we have. But more importantly, for TPV measurement, you are looking at having a black body source because you want to emulate the radiation photons at the rear site. So this black body source that we have is able to radiate photons from 500 degrees Celsius to about 1700 degrees Celsius. Reason why we choose this is because it covers most of the waste heat temperature that we are interested in. So we have that for us to do the characterization. Now, in terms of simulation work, we have also looked at some simulation work because we can't really do much semiconductor growth in Unit 10. We have subcon it to University of Sheffield for the growth. But in terms of simulation work, we have created a model for indium gallium arsenide, and we have carried out several different types of design variable optimization in what we call a multi-dimensional optimization using genetic algorithm. So I think nowadays everything is surrounding AI, and we realize by using a GA, it can really make our multi-dimensional optimization becomes much easier. Instead of doing 20,000 of iterations, using a GA, we are looking at reaching the convergence within 550 iterations. So in terms of the optimization, we were looking at minimizing the electrical loss, minimizing the optical loss, because these are two main losses that we want to reduce in order to increase the efficiency of our TPV cell. So by doing that, we maximize the absorption and also the conversion of the photon. Very similar to the solar cell, you are looking at the open circuit voltage, you are looking at the short circuit current. So VOC, ISC, again, these are very normal and familiar measurement that the solar cell is doing. It is just that we don't use AM 1.5 or AM 0 spectrum as in solar cell, but we are using a black body source as our spectrum optical source for that. So from that, because of the limited reported work on indium gallium arsenide TPV, most of them were doing optimizing using a single component or single parameters. And that is the reason why when we incorporated the genetic algorithm and when we did waste heat temperature from 800 to 2000 Kelvin, we were looking at the cell increasing by an average of 13%. So that was a huge improvement in terms of efficiency of the cell. If you look at solar cell, probably, it's quite a saturated field right now. If you increase by 0.5%, that was fantastic. But in this case, we were looking at such a huge improvement. Reason is because of a few fundamental things that was not explored. And when we were able to correct them, such as in terms of the thickness of the structure, in terms of the doping, we were able to get a significant increase in terms of the efficiency. So from that work, certainly we have some publication, and also we file a patent for that in terms of the method and also in terms of the highest efficiency that we got for indium gallium arsenide TPV cell. Right. Some of the other work, right? Again, this simulation. I won't go into detail, but some of the other work that we had is in terms of the illumination intensity. So if you are working in the area of solar cell, I suppose you are also very familiar. The efficiency of the solar cell can change with respect to the illumination intensity, or sometimes you call it a power density. So in terms of that, we also have done quite a good study on that, and we show that how the efficiency changes at different temperature when you change the power or the intensity. Very similar to a solar cell, we were looking at increasing the intensity can increase the efficiency of the cell, but only if the cell is fully optimized. Then when you increase the intensity, it becomes much faster in terms of increasing efficiency. So those were some of the minor research outcome that we got. Obviously, in that, again, I won't go into detail. You want to look at how you can fully optimize your series resistance and also the shunt resistance of your cell so that your fill factor will not be affected that much with increasing intensity, so that when you have an optimized in-gas cell with an increase in intensity, you get the optimized efficiency of the cell that you have. Now let's go into some of the experimental work, right? We realized after studying gallium antimonide, because it's a commercial cell, so you can buy it anywhere. We did indium gallium arsenide, which have very similar band gap. Yeah, it's had a very similar band gap, but we know the limitation where it can only harvest photons up to about 1.7 micrometer or about 1,700 nanometers. In order to overcome and make the cell more efficient, you can only push the cutoff wavelength to longer. So we also continue to work on indium gallium arsenide, but in this case, we changed the composition of indium to be higher and gallium to be lower so that the band gap can be adjusted to even lower band gap of about 0.55 EV and also to about 0.47 EV. These are the two composition that we had. Previously, the lattice match in-gas was having a 0.74 EV. That's why the cutoff wavelength was at about 1,700. So by doing that, what we will need to do with this new material is not really entirely new. This material were used in photo detectors, but it's not common in TPV cell. So we do it there. And what we really do with these two structure is that we can then be able to push. Initially, your in-gas is here, but when you change the composition, you were able to push the cutoff wavelength to about more than 2.5 micrometer or 2600 nanometers. Therefore, you are able to harvest this part of the spectrum that's supposed to lose if you are just using a gallium antimonide cell. So this is the motivation behind that, but we need to have or do a fundamental characterization on that. And that's the reason why we have some of our postgraduate students to University of Sheffield to do some measurement over there, and also most of the growth and fabrication were done there. So these are some of the setup that they did. Basically, what we need to do is we need to characterize indium gallium arsenide at different band gap to know their response to every single photons at different wavelength. So by doing or by measuring the photocurrent and also photo response from 1300 to 3000 nanometers, we were able to then know how much it will absorb in terms of the TPV photons. So from there, then you can do a back calculation on the estimation of the TPV cell efficiency. So for now, we have completed that in terms of optical characterization. We have completed the absorption coefficient. So you know how much it will absorb at a particular wavelength. So you know how much it will absorb at a particular wavelength. And because of the complexity of the equation, again, we need to use some of the AI technique to solve for this absorption coefficient. Currently, honestly, we don't have a TPV cell, I mean, a real TPV cell, optimized TPV cell at this particular wavelength. But from the fundamental characterization and the absorption coefficient, we can easily do a back calculation and say, what is the possible efficiency if we are able to grow certain, at a certain thickness and a certain doping and so on. So this was another work done and to be published later on. So those are completed work, and what are the ongoing work that we are currently doing is that initially we are looking at binary product or only two elements, gallium antimonide, and that was the initial or first commercialized TPV cell, I would say. But in our previous research work in the last 2 years, 3 years, we were looking at ternary compound, indium gallium arsenide, because we can adjust the band gap from 0.74 eV all the way to about 0.4647 eV so that we can extend the cutoff wavelength. Now, we have a few ongoing work, which is looking at quaternary compound together with University of Lancaster, where they were helping us to grow some of the indium gallium arsenide antimonide devices for a few reasons. You may say that you are having a 2.5 micrometer, which is about 2500 nanometer cutoff, very similar to the InGas. But we were looking at how we can grow this kind of quaternary elements onto, or quaternary compound onto a gallium arsenide substrate. That will then significantly bring down the cost because you can get large area substrate at a much cheaper cost if this can be done. So we were also, and we are currently also looking at how we can again go for indium gallium arsenide antimonide up to about 2,900. The latest sample that we have is a 2,900 nanometer cutoff. So this is a little bit of the design where you need to have some buffer region because of the lattice mismatching. But with that, a little bit of buffer region, you will be able to grow on a gallium arsenide substrate on this. So this is one of the ongoing work done by Andrew Marshall. He's one of our collaborator from Lancaster University that is doing the growth together with his team. Right. If I just do a very quick summary, I would say compared to solar cell, certainly we know that there are many groups doing on solar cell. TPV certainly is not explored by many research group. We are looking at, if this can be further explored and further work can be done, certainly we can achieve much more. Currently, our work is focusing on these three types of indium gallium arsenide. We can see the potential because you go higher, longer cutoff, you get much more photons, but at the expense of lower open circuit voltage. So that is something that you want to take note, how we can maintain that open circuit voltage. Of course, there is a theoretical limitation, but increase the short circuit current in a much faster rate by extending the wavelength. So that is our work that has been completed, but we are still working on that. Ongoing work on indium gallium arsenide antimonide. So ongoing characterization work for this new material. Some work has been done by some other group, but there is still a lot of work to be done in this area before we can confidently grow a TPV cell. Certainly to commercialize the product, we started off in the introductory slide saying that it is 30 years later or slower than a solar cell. If solar cell is the king in the last 2 decades, I would say, probably in the next 20 to 30 years, hopefully we'll see TPV will be there if we can work towards commercially viable application. So we are talking to a few industry such as Petronas, TMB, for some of the possible application, and with the support and also funding from all these giant company, hopefully we can make a good advancement in the future. With that, I think just an acknowledgement to the research group and also the team before we end. Thank you. And also the University of Sheffield and Lancaster for their growth and fabrication of the cell for us to do characterization. All right, thank you very much. And we welcome any question and also discussion either during this session or after that also is very much welcome. Thank you. Yeah. Yeah, exactly. Uh, until now, we don't see, at least in our country, because again, the cost is a major problem. That's why people needs to look at very cheap material. Germanium is one of the very good material, but in Malaysia, at least for now, we don't see any application yet. Yeah. 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 Right. So you were saying some 38 degrees Celsius. So it's almost, is that? Yeah. So if we look at the spectrum, right? So you can see that if we were to, can I just go to the slide that we have in terms of spectrum? Okay. If you see the spectrum, the overall power of the spectrum will reduce quite significantly with reducing temperature. So this slide is just showing you that, this is 1800 Kelvin. The area under the graph represent the amount of power. So by the time you drop to about 800 Kelvin, it is still quite high. It's not very low, but it is already quite low. So, and also another thing to take note is that as you lower down the temperature, you are looking at the peak wavelength shifting towards the right. So which means you need even narrower band gap to capture that heat. At least until now, TPV has shown some capability down to about 500 Kelvin to harvest some useful power. But to go to 38 degrees Celsius, which is probably 300 plus Kelvin, is a little bit quite impossible. Reason is because you need almost like a conductor instead of a semiconductor to harvest that. So can you harvest? You can still harvest, but is it high enough? Definitely not. So yeah. But if you talk about the condenser and also some of the part in a thermal power plant, just to discuss on that is that the condenser part is designed in such a way, is towards the end of the cycle, right? So they have done some, what do they call, is recycling of the heat. In thermodynamics, they have terms on that, but I can't quite remember. So they will recycle until it goes to very low temperature. So that is the heat and temperature of the steam that they have. But if you look at the area where you burn the coal or you burn whatever fuel that you have, the waste itself can have a temperature of almost 900 degree, for 500 degrees Celsius to about 900 degrees Celsius type of waste heat. So that should be our focus instead of going to the other end of the steam temperature and also water temperature. Yeah. Yeah. Mm-hmm. Yeah, so that's why in most of our work, we were looking at using the correct band gap, the material with the correct band gap. Reason is because if you have a correct band gap, in the first place, you won't lose the photon. So if the photon is not lost, they are converted into electric in terms of current. Now, if you want to minimize the losses, there are a few main things. Probably if I show here, when you have a metal contact on top, even in a solar cell is the same thing. You want to minimize that so that you can optimize the photons that is falling onto your semiconductor. So that is first thing. But you also at the same time do not want to lose the electrical part, because if you make your contact too small, your series resistance become too high, your field factor is affected. So that's why we need to do a multi-dimensional optimization so that every parameters are taken care of at the same time. If you were to look at one parameters, certainly it's easier. You can just push to the best, but you will see that that best giving to that particular parameters may cause bad consequences on the other parameters. So there are several of them. And the other part of reducing and minimizing the optical loss will be in terms of the thickness of the device, because the longer the photons penetrate through your structure, you will be able to capture them more efficiently. But you do not want it to be too thick such that most of them are absorbed in the region that you don't want. because they can absorb throughout your structure. But the other important part is after they are absorbed, they will convert into they will convert into electrons and holes, but in the end, are they reaching the other end of the junction to create that electricity? So a few consideration in terms of electrical and also opticals are important for us to overcome this issue. Right. Yeah. Yeah. Sure. Yeah. Can I stop sharing first? Right. Right. Thank you. Okay. See you. Thanks.